open system, and I think this is the last what we discussed. That area under the TS plot gives you
Heat
TDS is
transfer.
heat transfer Q. Okay. Now let us talk about disorder. Okay, so there are some questions which we had earlier that we'll try to answer today, and basically we will talk about how second law gives direction to natural processes and what is the role of entropy. So as you can see that there are three states of matter: solid, liquid, and gas. So which one do you think is higher order? Which is more ordered configuration among these three?
Solid, sir.
Solid.
Solid.
So solid molecules or atoms also vibrate or move about in their mean position, but more or less they are sticking to the same position. Whereas liquid and gases, they have more tendency to move. They have more space and they have a larger area through which their molecules can move. So this is the gases have more disorder. They can move randomly or they can move freely to a larger extent, much larger extent as compared to solid. Now the question is which has higher entropy, solid or gas?
Gas.
Gas.
Yes,
Yes.
because it has more disorder. So there are more number of micro states that can be formed. So I say that gas has more entropy. Another example, what you can see is that if you have a substance which has magnetic, let us say, molecules or particles, and if you apply a magnetic field, they all will align to that magnetic field. Okay, they will align in the direction properly. Now, if you remove that magnetic field, they will disorientate. They will get aligned in different directions. So, which one is having a more ordered state? This first or second?
First.
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 So, is we apply magnetic field and we get a more ordered state or less chaos. And if you remove magnetic field, if you don't do some external, use some external agency to apply magnetic field, then naturally they occur in random states, which is more disordered or has higher entropy. So in a crude way, we can see how the second law is getting applied. So a natural state is that substance will go from ordered to disordered state and not the reverse. Okay, they are not aligned themselves unless you apply some external force. So that is how nature works. That is how things go from order to disorder or increase in entropy. Okay, let us take another example. Let us say that I have two objects, let us say two metal blocks, so which have different temperatures. Okay, now I bring them in contact. So what will happen is after some time they will be equilibrated. So both the temperatures will be same and they will attain some average temperature. They should be average temperature. Okay. Similarly, if I have two different gases separated by a partition, that is not shown here, it should be something like this. So if some partition is there, I remove the partition, then these gases this will mix. Okay, so this is the natural direction. This is what is allowed by the second law, or this is what the second law arrow of we'll talk about time also. So this is the natural way things proceed. Okay, what about the reverse process? Reverse does not happen. Two metals will not separate themselves and they will say they will not have different temperatures. This is the natural direction. This is not. Okay, similarly, mixing is the natural direction, unmixing is not. If you leave it for any time you want, the gases will not separate automatically. Okay, so if you remember initially when we discussed the second law, this is what we are referring to. That what are the processes which are spontaneous or natural. So the forward is spontaneous, the reverse is not spontaneous. This is not natural. If I want to do this, I have to apply some external we have to give some work or any method, but naturally it will not happen. That is the whole idea. Now, second law basically says that entropy of the universe is increasing. So whatever process that take place naturally, all the processes have this direction. Okay, they will try to increase the entropy of the universe. They will try to be more disordered state. Okay, and entropy, as we discussed, can be understood to be the degree of molecular disorder. And when you add heat to the system, it increases entropy, it increases molecular disorder. That we have already seen even in the numerical form, that ds is equal to dq by t. Okay, now we'll not go into detail. This is a little complicated subject, but Boltzmann defined entropy by attaching each state to a thermodynamic property. So basically called macro states. Okay. So we said that different arrangement has different probability, and if you want to calculate entropy, I can use this equation where n is the number of macro states. Okay, n is in a crude sense, you can say that it is the number of ways in which the molecules can be arranged. There could be different permutation combinations. So what all we can do with the given system, that all has to be accounted for, and that will give you n. And K is the Kb, actually it should be Kb. Kb is the Boltzmann constant, and this gives you entropy in absolute terms. Okay. So this equation is so important. So this is Boltzmann's tombstone. So when someone dies, the most important contribution or whatever he has done is engraved on his tombstone. So this formula is actually written on his tombstone. So instead of I have used n, he is using W. W, or some books you'll see that a symbol like this will be used. So these are all for macro states, number of macro states. So now let us talk about time. So as I mentioned that in this book, Brief History of Time, Stephen Hawking talks a lot about space and time and how entropy is related to time. Okay, so for example, when you have a cup which falls from a table and gets broken. So what it says that we don't see that broken cup gathering themselves. It will not come back to your table and jumping back onto the table, because that is forbidden by second law. It goes against the second law. If that happens, it will decrease the entropy. Okay. So what it says is that in a closed system, disorder or entropy, is using the same word, always increases with time. So this is what we have learned in the second law, and this is what gives you the arrow of time. This will give you sense of time. Okay. So a intact cup is high order state, but a broken cup is disordered state. So this has more entropy. And one can go readily, basically you can go in a direction where entropy is increasing, but not the other way around. You cannot join this cup parts and make a full cup naturally. Okay. So basically what he concludes is that this gives you, this entropy will give you arrow of time. Okay, it will tell you the direction in which natural processes proceed. So for example, if you make a video recording, okay, and if you play the video in reverse, you can see that cup is coming back to the table, right? But that does not happen naturally. So the cup and table are a very common example that you know, but suppose there are some chemical reaction or some phase changes happening. So if you're not very sure that what process is going to proceed, whether you're looking at the video forward or backward, then you have to consider entropy. So entropy will give you a sense of time. Entropy will tell you which direction entropy is increasing. That is how the time will go. That will give you arrow of time. Okay, and that is also true for the whole universe. So at some class, someone was asking the question that what is the maximum limit or how much entropy will grow? Is he present today? Someone asked that question, right? Uh, what is the maximum limit or how much entropy can grow? So basically, what we know, you people are here or not?
Yes,
Yes,
sir, we
sir.
are here.
Yes, sir.
Okay,
Yes,
fine.
sir.
Yeah.
Yes, sir.
So,
Yes, sir.
okay, so let me just briefly talk about this and then we'll wind up. So, someone was asking whether how much entropy can grow. So, for a system, okay, when you have system plus surrounding, we one rule is that we'll say that when the system comes in equilibrium with the surrounding, that is the maximum that we have discussed a few class ago. So there we say that entropy reaches maximum and the maximum entropy is at the equilibrium. Okay. Now for the universe, there is no surrounding. Everything is inside the universe. So the general understanding is that the entropy of universe is at the Big Bang it was minimum and then it started to grow, and basically it is showing separation between two galaxies, but this is also true for entropy. So entropy of the universe is increasing with time. That is what we generally understand. Now there's one more model or one more possibility that was proposed by Stephen Hawking. So he said that entropy of universe can also grow and can also come back. So he says that it will everything will collapse back to a single point and then we'll have a big bang again. So that is something of a science fiction, but we limit ourselves to here. Till present, whatever observation we have, it shows that entropy is so far increasing. We have never seen any example that this will go down. But this is one possibility or one proposal given by Stephen Hawking. In general, we'll stick to this. Okay, so in fact, if you look at this image, this is from NASA. So just read the last line. From an homogeneous and orderly state, entropy increase over time. Okay, so far we have observed that entropy is constantly increasing. Since the Big Bang, the entropy of the universe is always increasing, and with the topics that we study in this subject, we hope that will indefinitely happen. That will always be true. That entropy of the universe is it will keep on increasing, and that will give you the arrow of time. Okay. Now let us talk about absolute entropy. Okay, so for a pure crystalline substance, okay, without any defect or any disorders, if you take that to absolute zero, okay, 0 Kelvin, then that is a state of perfect order. Crystalline substance arranged, the molecules or atom will be arranged nicely in a crystalline order, okay, without any defects. So there are also a lot of defects in arrangement of solid crystals. So we assume that nothing of that sort is there. It is perfectly ordered, and if you take it to 0 Kelvin, then it is called a perfect ordered state, and the entropy is defined to be zero. Okay, but generally that is generally we talk about the difference in entropy, but absolutely this is how it is defined. But there is another challenge here that absolute zero temperature is not attainable in finite number of operations. Okay, so basically it says that you cannot go to absolute zero. You can be like 1 or 2 degrees above that, but you cannot reach absolute zero practically or theoretically also. The absolute, that's why it is not possible to attain absolute zero entropy. Okay, so this is called third law of thermodynamics, and this statement is given by Nernst and Simon. So basically what it is telling is that you cannot achieve 0 Kelvin and you cannot achieve zero entropy. There will always be some entropy associated with the system, but it doesn't bother us much because generally we are using delta S. We are using change in entropy, and we are not much concerned with absolute entropy. Anyway, we also define some reference points. So we say that, okay, at room temperature or HTP, this is the entropy based on our calculations, and then we can take delta S. Is this clear to everyone? What is absolute entropy?
Yes, sir.
Okay. So now let us look at some relations of entropy, and basically we'll try to combine some results from first law and second law. So this is how we define entropy for a reversible process. Delta Q is equal to TdS. Now I can also write TdS if I combine this with the first law. So first law says dq is equal to du plus pdv. We are assuming only pdv work. So if I combine these two, instead of dq, I'll write TdS. So TdS is equal to du plus pdv. I can also write this in terms of dH. If you remember, H is equal to u plus pv. So dH will be du plus pdv plus vdp. So if I take this term, then this is equal to dH minus vdp. Okay. dH can also be written as cpdt. So if I combine these two, I can write, so take T from LHS to RHS, it will divide. So ds will be equal to, so if you look here, dH will become cpdt divided by T. cpdt divided by T minus vdp divided by T. So this is one equation for ds. Now if you integrate this, suppose I want to, basically we are interested in delta S. What is the change in entropy for a particular process? So for that I can also use, okay, I can also change this form by using this equation of state. So I can also write ds is equal to cp dt by T minus, instead of vdp by T, I can write r dp by P using this. You can try this and see. Substitute PV is equal to RT in this part and you will end up with r dp by P. Okay. Now we have two equations. Now we want to integrate. So if you integrate between 1 to 2, we'll get delta S Cp of log of T, because we have T in denominator, log of T minus R log P, P2 by P1. Also, I can substitute du as CVDT. So if I have that, I can also say that delta S is equal to Cv log T2 by T1 plus R log V2 by V1. Okay, so these are the two important relations which we can use to find entropy for a given process. So if you have what are the final and initial temperatures and pressures or volume, you can use this to find delta S. Okay, we'll talk more about TDS relations in the next chapters. We'll also discuss something called Maxwell relation. So there TDS will be discussed in more detail. But as of now, for this chapter, these are the two relations. In fact, you can use maybe PVRT or some other gas relations to calculate delta S. But these are the two basic forms that will stick to. So lastly, one more topic I wanted to, and then we'll wind up. So basically, if you have TDS is equal to DH minus VDP, that we discussed in the last slide. Now, if you use a steady flow energy equation and you neglect kinetic and potential energies, okay, so I can write work done in that cycle or in a process as dash, which will be equal to minus of VDP. So generally we talk about work in PdV, but by using entropy, we can also see that for an open system. Okay, this is especially true for open system when we are using steady flow energy equation. So we can get work by integrating VDP like this. So this is your process from 1 to 2. So if you integrate area under this curve, area with the y-axis, this area will give you work done. Okay, is this clear or any questions you have? With that, we'll stop with entropy. So any questions we can